Hello everyone and welcome to a new video of this course of reservoir simulation. Let's continue with the fluid flow equation in porous media. As you know, we are interested in reservoir dynamic simulation. In the previous video, we focused on the mass and momentum conservation equations and on the constitutive equations for both porous materials and fluids. Now we continue defining how to characterize the fluid model. In general, two possibilities are considered: the black oil model and the compositional model. It is also very important to know whether we are working in a reservoir or in standard conditions. What are the differences between the two models? When do you use one or the other? The black oil model is a simplified, faster, and generally used pattern. It contemplates three phases: oil, gas, and water, with a single component in each of them. For the oil phase, can have one component, oil, or two components, dead oil and dissolved gas. Sometimes gas condensate reservoir simulations can be developed also with this model. If there are, and we are, interested in the changes that occur in the components when changing the reservoir conditions, we will use the compositional model. It makes a component description in each phase, being able to change the present components when changing the conditions of the reservoir. The mass balances are made for each component, for methane, ethane, propane, and so on. In this slide, you can see what happens when the oil migration does not find a seal formation. Then the oil reaches the surface. You can see the dissolved gas bubbles that are released with the pressure change. When this happens, some formations appear as an ant hill that in Venezuela are called mené. In the phase diagram of the slide based on Moreau, you can see the critical point C, the bubble curve on the left and the dew curve on the right. Above those curves would be the initial conditions of our reservoir, being able to be initially oil, that is dead oil, black oil, and volatile oil, or gas, condensate gas, wet gas, and dry gas. We will use the black oil model in those regions in yellow of the diagram in which we can assume small variations in the composition of the components. For example, if black oil is our initial conditions, we will be interested in maximizing the production path for as long as possible over the bubble curve, and thus not lose the trace of the gas that is dissolved in the oil. Now let's look at the parameters that define the black oil model. The two most important are the amount of gas dissolved, R is, in a unit volume of oil and formation, and the second, the formation volume factor B. It is very important to realize that the RS is defined in standard conditions, whereas the B is the ratio between the volumes in reservoir and standard conditions. B is always greater than or equal to 1 because the oil in the reservoir occupies a higher volume than in surface, where the gas has been released. Never forget what unit system, international system, field, or lab system you are working on. This is a very common source of errors in the simulation. Other properties we need in our black oil model are compressibility, viscosity, and density. Considering that there is conservation of mass, we can express the density of oil in reservoir conditions, ρO, as a function of B, R is an oil and gas densities in surface conditions, that is, ρOS, ρGS. Note that the oil density under surface conditions, ρOS, is the sum of the surface density of both oil and gas dissolved in it. In the case of gas dissolved in the water, we would consider the R is W. In this slide, you can see the evolution of each of the parameters of the black oil model with the pressure. The bubble point pressure, PBO, separates the saturated region from the undersaturated one. Above the bubble point pressure, R is constant. All of these curves obtained in laboratory tests will be incorporated in the input files of the simulation codes. Now we can include the parameters of the black oil model in the flow equation described in the previous video. For single-phase system, the density in the reservoir conditions can be expressed as the ratio between the density in surface, which is constant, and the formation volume factor B. If we assume, following the approach of John Klepp, a single-phase flow, oil, gas, or water, in one-dimensional horizontal system, isothermal conditions, Darcy's equation, and a constant flow cross-section area, the flow equation becomes the expression that appears in this slide. Compressibility is the sum of the compressibility of the porous media and the fluid. Remember that this is the expression of the flow equation for the simplest case in one dimension, where we only have one phase and one component. For who would be interested, in this slide you can observe the steps given when performing the time derivative of each variable. In the next video, we will see what needs to be done to work with the flow equation when there are no exact solutions to the problem posed. In this case, we will look for approximate solutions, and for this, it is necessary to realize a spatial and temporal discretization of the flow equation. So, thanks a lot. I see you soon.